Hello, my name is Victoria Grimes, and this is my Lab 4 over oscillations in a spring mass system. The purpose of Lab 4 was to observe the motion of a mass swinging in an arc while oscillating on a spring, measure the motion with the tracker application, construct a computational model based on the foundational principles and initial conditions, compare the models with observations, and draw conclusions about the energy principle. Our goal was to determine if the model satisfies the energy principles, and the result was that the total change in energy of the system remained equal, meaning the energy principle was satisfied. Some fundamental principles and models in Lab 4 were Newton's second law, which relates the net interaction between system and surroundings to changes in the momentum or motion of the system, and it also says an object's change in momentum is dependent on the net external force, and we also use the velocity update formula and the position update formula in the code. Another fundamental principle we used was the energy principle that says the change in energy of the system is equal to the work done by the external forces and the amount of heat gained by the system or lost to the surroundings. Types of energies we can have on the energy side of the equation are kinetic energy, potential energy, and thermal energy. For this lab, only the kinetic and potential energy, specifically gravitational and spring energy, are important. Considering the Earth, the mass, and the spring in our system, the work by external forces is 0. We also have the spring force equation here, where S represents the compression or expansion of the spring in relation to the relaxed length, L naught, and this is also a non-constant force. And some general concepts is that we're using translational kinetic energy because we're using a point particle system, and also presented here are the equations for gravitational potential energy and spring potential energy. Shown here is a sample calculation to derive the initial conditions for the spring, such as the length L. The video on the left is a simple video of someone releasing a mass attached to a spring from rest. The video on the right is where I put the footage into Tracker and calibrated it to get the position and time information I later put into the computational model. I inserted this data into the computational model based on data I received from implementing the Tracker application. The bottom right photo is a graph of the X position graph in Tracker. The X and Y position values were copied and pasted into an Excel and saved as a CSV file, which was then read into the computational model. For the code, I inputted the information from a previous slide into WebVPython to create this computational model. As you can see on lines 124 and 126, the update velocity and position formulas were used to calculate the velocities and positions at each timestamp. Furthermore, the potential energies were calculated in lines 107 to 111. The energy changes for each energy type were calculated inside of the while loop. These are the computational model results for the X and Y positions. The red line is the experimental data and the blue line is the model. So now's the time for conclusion and discussion. Was the energy principle satisfied? Yes. There are no surroundings, which means the total energy is 0, which is consistent with the orange line on the graph. The kinetic energy oscillates between positive and negative values as the mass gains and loses energy in the blue line, and the potential energy due to gravity and the potential energy due to the spring are inversely related with roughly equal magnitude, oscillating within the same time phase. Also, using the data I obtained in Tracker, I made 2 separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data, and then comparing the 2 estimates. So, to do this, you observe the time difference between 2 mins and maxes on each position versus time graph. The X position data gave us a time of 1.59 seconds, while the Y position data gave us a time of 1.37 seconds. And the question is, why are they different? Well, the mass is moving in 2 different directions, thus having different behaviors. In the Y direction, the mass is behaving like a spring, and in the X direction, the mass's motion is like a pendulum. Now to address some experimental sources of error. First, the system is not actually closed, and therefore, there are other unaccounted forces acting on the system, such as air resistance. Also, Oscillation periods were a rough estimate, and this means that they're not very accurate.